Hi guys, let's go ahead and talk about section B5. This is the third section that we've covered. This one covers rational expressions. You should be looking at your notes as we go through this together. You'll see the beginning of the note states that a rational expression is a ratio of two polynomials. We've talked about polynomials. We know that polynomials are it's like a collection of terms, and each term might have a variable, might have an exponent. So polynomials can look like just maybe x minus 3. A polynomial, this one up here on the top, would be a trinomial. This x squared plus 2xy plus y squared. Alright, so all of these are polynomials, and the rational expression just indicates that they are, you've got a fraction that's comprised of polynomials. So these are what rational expressions look like. These are just examples of what we'll be working with. We start with the definition of domain. This is very important. So let's read this together. The domain of a rational expression is the set of all real numbers that can be used in place of the variable. In other words, that means the domain would be any number. The domain would include any number that you can put in for x or for y and get a legitimate answer back. So you can think of it as inputs if you want to. For example, in my very first example here, I'm looking for values that I could put in for x. So, I could put in a 1 and I'd get an answer back, etc. Let's look at example 1 part A. We want to find the domain here. Alright, so we have to be careful that we're thinking about possible restrictions on our x. In this piece, or in this example, there is a restriction on our denominator. It is possible to put a number in for x that will give us what we would consider an undefined answer. You might know what that is, or maybe you don't. I don't know. But the key here is to think about what value. Basically, if you look at your notes, you'll see that I've got a reminder that we know from arithmetic that we cannot divide by 0. So that just simply means that let's just talk about that for a moment. Just going all the way back to when you first learned division, a long time ago. If you were asked to do something like 7 divide by 0, let's just see what would happen if we tried to do that. So if you were to set up a division problem, you would do you'll do 7 divided by 0. This is asking us to find a number that we can multiply by 0 that would give us this number on the inside. And hopefully you see that that is a problem. If you try to multiply any number by 0, it will always equal 0. So that's why we have this rule that we can never divide by 0. That's a very important rule to remember. So we're going to think about this up here. We have to be careful that we do not put a number in for x that would give us a denominator of 0, because that's the same thing as dividing by 0. So what number would I not want to put in for my x? In other words, what value of x would we think of as a restriction? If I put in -3 for x, then that would give me a denominator of 0. So I can say that my domain is every real number except x cannot equal 0. So we'll say our domain is all real numbers except all real numbers except -3. Alright. Or it could also be written as this symbol means all real numbers, comma, x cannot equal -3. You might also at some point need to use set notation to express your answer. If you did, you would just say the set of all elements x such that x does not equal -3. It just depends on which way you're asked to do it in my math lab. As far as I'm concerned, this answer is perfectly acceptable. You're telling me that it's all real numbers except x cannot equal -3, and that's good. What about part B? It's the same concept here. We've got to be careful that we're essentially looking for any value of x that would give us 0 in our denominator. So because this denominator is a little different from the last one, because this one could not be factored, but x squared minus 9 can be factored. So let's go ahead and factor that first. So we've got x plus 4 over, and then we know that's a difference of squares. It factors as x plus 3 times x minus 3. Once it's factored, it's a lot easier to see what values of x would give you an undefined answer. We can see that if we put in negative 3 here for x, or if we put in a positive 3 here, either one of those would give us a 0 in our denominator. So we can say that our domain is all real numbers, but x cannot equal 3 or negative 3. All real numbers, x cannot equal 3 or negative 3 is our domain. So we're ready to talk about example 2. We start on our second page of notes discussing the basic principle of rational numbers. That simply states that if you've got basically any fraction, and you've got the numerator and the denominator both factored, so you've got 2 factors in the top and maybe 1 or 2 factors in the denominator. If they share a common factor, then we can reduce and just basically cross out that common factor and replace it with 1. So let's look at part A. And it should be this, excuse me. So part A, we're asked to reduce to lowest terms x times x plus 1 divided by x times x minus 3. Okay, so you can see that we've got a common factor of x on the top and in the bottom because it's being multiplied to all this other stuff over here. So because these are being multiplied, we get to reduce. And anytime you've got any value divided by itself, it always gives you 1 because anything goes into itself one time. So you can cross these out and just replace it with 1. And then our answer will be the x plus 1 over x minus 3. For part B, again, you're looking for a common factor that both the numerator and the denominator share. This time they share a common factor of x minus 5. So we can cross out these 2 factors and just replace it with 1. And that just leaves us with x plus 2 over x plus 4. How is part C different from the ones that we've just done? Part C has a little bit more work. We have to see if anything can be, we have to go back and look at the rule again. Notice that it states that you have to have factors being multiplied to each other before you can reduce. So this is a very common mistake that people make all the time. You cannot reduce anything here because we do not have factors. These are all separated by pluses. That makes them terms. And it also makes sense if you think about when you reduce, like we did back here, we essentially divided something by itself, and it makes sense that division would undo multiplication. So they have to originally be multiplied together before you can undo the process with division. So let's see if we can get this numerator and this denominator to factor for us. All right, in the numerator, 2x plus 4, that has a common factor of 2, so we can pull that out. That leaves x plus 2. Our denominator is a trinomial. Alright, so you're going to think about, if you want to think of a times c, your a is 1, your c is 6. So you need factors of 6 that you could add or subtract to give you your middle term here, 5. It might not be obvious at first glance, but also pay attention to your signs because everything is addition over here. You need to find a pair of factors that have the same sign, and then when you add them both with the same sign, they would give you your 5. So we would need to subtract the 1 and the 6 to get a 5, so that's not going to work. We can go with the 2 and the 3. And if you could rewrite it using the grouping you could rewrite it in the factor using the grouping method. But what I would do here, just notice that if your a is 1, the numbers that you get here are the same numbers that will go into the parentheses after you go through the factor by grouping process. Okay, so again, because a is 1, I can just go ahead and say that my factored version is x plus 2 times x plus 3. Okay. Again, if you struggle with factoring, please know that you are not alone. we should have ample time in class because we're doing these video lectures that I can answer any questions that you have. So please don't hesitate to ask me if you're not seeing. As you're going through your notes, just mark it so that you don't forget. And then when you come to class, when I get an opportunity, show it to me, and I'll be happy to look at it with you. All right. So we see now we've got a common factor of x plus 2 over x plus 2. So these can be reduced, and we are left with 2 over x plus 3. Alright, you probably noticed that I'm at home in this video, so I'm going to have to erase the board before I can finish this problem because I've got a smaller whiteboard here. Okay, so for part D, we're asked to reduce the lowest term, so we've got b minus a over a cubed minus b cubed. The a cubed minus b cubed should look very familiar to you. That is a difference of cubes. It also happens to be the exact same letters that are used in the formula, so this should be really easy to factor. If you may not remember the formula off the top of your head, but make sure you do know it before your first test. But our difference of cubes formula a cubed minus b cubed equals a minus b times a squared plus ab plus b squared. Okay, so that's what we're going to be substituting in that second line. So in the top we've got b minus a, and in the denominator this factors as a minus b, a squared plus ab plus b squared. Alright. What about that trinomial? Do I have to try to get that factor? No, I don't. I do not have to worry about factoring this because this is the result of the factoring formula that was given to me. If it factored further, the formula would compensate. It would tell us if we needed to go any further with it. So I don't have to worry about factoring this trinomial. Looking at this, what do you notice? We've got b minus a over a minus b. This is that situation that we discussed before, where you've got the same terms but the signs are opposite. So do you remember how we can fix that? This is when we can factor a negative 1 out of one of these factors. When I say factor, I'm looking at that entire numerator as one factor, and I'm trying to see if I can get it to reduce with the a minus b factor in the denominator. So if you recall, we can factor negative 1 out. All it does is change the signs, and it makes the two factors identical. So we can go ahead and cross this out and just replace it with a negative 1. Alright, if you don't know why, ask me during class and I'll be happy to talk about it more with you. But we also discussed it extensively in it's either the first video or the second video, I'm not sure, so you should have seen it somewhere. Alright, but anyway, we can cross out these two factors and just replace it with negative 1. So our answer is negative 1 over a squared plus ab plus b squared, and again we don't have to try to factor that denominator because it came from our factoring formula. So that's our answer for part D. So we're going to talk about multiplying rational expressions. Before we do that, let's just take a moment to review some basic fraction operations that you may be, sometimes people are a little rusty on these. When you multiply rational expressions, you're following the same rules that you followed when you multiplied any fractions. The rules for multiplying fractions are really simple. They're the easiest ones that we work with. When you multiply fractions, you just multiply straight across the top and straight across the bottom, and that's all you have to do. Sometimes you might need to reduce, but other times you may not have to. So looking at my first one, 2/3 times 5/7, if you look at the 3 and the 5, look crosswise, do 3 and 5 share a common factor? They don't. 2 and 7, they do not share a common factor. So we can just multiply straight across the top and get 10 straight across the bottom. 3 times 7 is 21. 10 over 21, they do not share any common factors, so we don't have to reduce that. And we are done. In the second example, 3/5 times 10/9, this time I can reduce first. So that you could reduce at the end, but it's much more helpful to reduce before you multiply. And in the problems that we're going to be doing, you're definitely going to need to reduce before you multiply. So just looking crossways here, we have a common factor of 3. So that becomes a 1, 9 becomes a 3. And then 5 and 10 share a factor of 5. So 5 goes into 10 twice, and 5 goes into 5 once. So we're just left multiplying 1 times 2 on the top, 1 times 3 on the bottom. So our answer is 2/3. So we're going to follow those same rules for multiplying our rational expressions. So example 3, part A, we need to multiply 2a minus 2b over 6 times 9a over a squared minus b squared. Before we can start trying to, so let's take this one step at a time. We're multiplying fractions. We know that we multiply straight across the top, straight across the bottom. We also know that we need to reduce anything first if we possibly can. So in order to reduce, well, you could go this way. You can see the 6 and the 9, they do have a common factor of 3. So you could go ahead and reduce these two coefficients. Looking at the 2a minus 2b and the a squared minus b squared, we need to decide if that can be factored as well. Or excuse me, we need to decide if that can be reduced. In order to decide if we can reduce it, we need to factor it. So you'll get lots of practice with factoring when you're going through these problems in this section. So in this one, the first numerator, you can see we have a common factor of 2. So 2 times a minus b over 6. And then here we have the difference of squares. That's a plus b times a minus b. Okay, before we try to multiply, let's see if we have any common factors crossways. So a minus b and a minus b, we can reduce those. 6 and 9 we can reduce by a factor of 3. 3 goes into 6 twice. 3 goes into 9 3 times. And you'll also notice that we've got 2 divided by 2 now, which is just 1. So that can be reduced as well. So what are we left with? Our numerator, we have 3a. In our denominator, we have a plus b. Do you think I could do anything else to this? Alright, sometimes people want to cross out the a's, but remember we cannot cross these a's out because this a is a term, it's not a factor. You can only reduce the factors. So we're going to have to leave it just like it is. 3a over a plus b is our answer. For part B, we've got a very similar type of problem. We just have to do a little bit more factoring here. My numerator, x minus 1, that will not factor. Because it won't factor, I'm just going to think of the entire numerator as a factor. So if you want to put this in parentheses, that's okay. That just kind of helps you look at it as a factor. And then maybe in the denominator, after we've factored these trinomials, maybe we'll have an x minus 1 show up. In this denominator, x squared plus 4x plus 4, you think that one, see if you can factor that. As a matter of fact, pause the video here, go ahead and factor these and see if you can find anything that you can reduce. Okay, so let's see how you did. X squared plus 4x plus 4 factors as x plus 2 times x plus 2. Or you could say x plus 2 quantity squared, but there's really no reason to write it as a square in this at this point. Over here we've got x plus 2 in the top. That does not factor. So you can think of this as a factor itself. And my denominator, I need opposite signs, and I need my 3 to be positive and my 1 negative. So I didn't go through all the steps for the factor by grouping method on that, but hopefully you're able to do that on your own at this point. If you're not, I can show you some tricks, so just let me know. What can we reduce here? Alright, we've got the x minus 1s. They can cancel out. Alright, I'm going to ask you a question, and it may seem like a silly question, but sometimes people don't know. If you've got two factors beside each other, can you reduce those? The answer is no. These are being multiplied together. You only get to reduce if you're dividing something by itself. So you can reduce this x plus 2 with this x plus 2. Alright, I don't see anything else that can be reduced. My numerator is left with just a 1. And my denominator has x plus 2 times x plus 3 left. Okay, so 1 over x plus 2 times x plus 3 is my answer.